Okay, we're going to pick up now with topic number 11 in Unit 2, which is going to finish out the electricity part of the unit, the current electricity part. And then in the next week of classes, I should say, we will be taking a look at the magnetic or the magnetism part and the electromagnetism part. But right now we're going to take a look at the concept of electric power and the cost of buying electricity, in other words, buying electrical energy. So let's get started. So electric power, first of all. You may remember from Physics 2204 that power is the rate of doing work. Rate of doing work. And remember that work equals change in energy. So power then, for electrical power, power is equal to energy over time. Power equals energy divided by time. Or, another way to write that is energy equals power times time, but we'll get back to that in a second. So power equals energy over time. Now remember this expression though, E equals VIT, and we talked about that one in a previous class when we were talking about electric potential energy. Electric potential energy is voltage times current times time. So if we plug that into this equation for E, we got VIT over T, the two T's cancel, and we're left with this formula. P equals V times I. That is the formula for power, or at least one of the formulas for power. That formula is on your physics data sheet. P equals V times I, or I times V. I can't remember exactly which form of it is there, but it's the same equation either way. And we can use that equation in conjunction with the equation for Ohm's law to get a couple of other different expressions for power, because this one here is useful if we know the voltage and the current. It's easy to find the power. But what about if we know, instead of voltage and current, what about if we know resistance and current? Or if we know resistance and voltage? Well, we could use Ohm's law to find the third one and then use this formula, or we could do this. Okay, we could put V equals IR into this equation. In other words, replace the V with IR, and we get I times R, or I squared R. There's another possible version of the power formula. Now you don't have to use it. Like I said, you can use Ohm's law first if you want to find voltage, and then plug the voltage in. Right? If you were given current and resistance, for example, use Ohm's law to find voltage, and then use the power formula. So you can always do that. But if you want to do it all in one step, you can combine the two equations. We can do the same thing for if we don't know I. If we're given voltage and resistance, we can say I equals V over R, plug that in here for for I, and we get V over R times V, so V times V over R, or V squared over R. That's another way to write that same equation. In other words, we're combining Ohm's law and the power formula. Okay? We can do that. Now, like I said, you don't have to do it because you can always use Ohm's law first and then use the power formula. But if you're a fan of doing everything in one step, then by all means put the formulas together and use that. Now these two versions of the power equation are not on your formula sheet, not on the physics data sheet. However, P equals V times I is, and V equals I times R is there. So you can always do it that way. You can always do it that way. So here's some of the formulas. Right? Power equals energy over time, that's one way. Power equals I times V, or V times I, same thing. Power equals I squared times R, or power equals V squared over R. Four different ways to calculate power. And since energy and power are related, we already said that power equaled energy over time. We said that just a minute ago up here, right? We can rearrange that and say energy equals power times time. And because energy equals VIT, I can always substitute that in. VIT equals power times time. Or we can say this, energy equals I squared R times T, because that's power, right? Power is VI. or power is I squared R, or power is V squared over R. So all you got to do is multiply the power by the time, and you got energy. Okay? Now if you want to memorize all those, you can, but it's really not necessary. The only one there that you really need to memorize is this guy right here. That one is not given, but it's a very important formula. Energy equals power times time. Okay? Remember that one. Remember that one. Now, if we're purchasing electrical energy, what we're actually paying for is the amount of energy that we use. Okay? And everyone in their homes uses electricity in some form. Okay? You might use it for heating. You might just use it for lighting and other things. Okay? But everyone uses some electricity. And under the metric system, energy is normally calculated in megajoules. Right? Energy usually calculated in joules. And because joule is a fairly small amount of energy, we usually measure it in terms of megajoules. But even though many power companies in Canada do use that metric, in Newfoundland we typically use the old unit that was used before the metric system came in. They just haven't changed it. It's called a kilowatt hour. A kilowatt hour. Remember, kilowatt is a power unit, and hour is a time unit, so power times time, right? Kilowatt hours. And if you look at your light bill at home, you will see that the cost is given on that light bill as a number of cents per kilowatt hour. In fact, the amount of energy you use is actually given as kilowatt hours. Okay, now I think Newfoundland Hydro may do it differently. So if you live in Labrador and you're dealing with Newfoundland Hydro, it may be a little different. But I know on the island with Newfoundland Power, we do use kilowatt hours. So a kilowatt hour just means, and by the way, the current cost in Newfoundland as of May 2011, I just looked at my last light bill, is 9.584 cents per kilowatt hour. That's how much every kilowatt hour costs, about 9.5 cents. Not a terribly large amount when you think about it. And most things in your house don't use a whole lot of power. And we're going to do some sample calculations from tests now in just a bit. But anyway, a kilowatt hour just means that 1 kilowatt of power, or 1,000 watts in other words, but we have to change it into kilowatts, is used for 1 hour of time. That's the amount of energy in a kilowatt hour. 1,000 watts for 1 hour. And we're buying energy, not power. So we're paying for not only the amount of power we're using, but how long we use it. So it's actually energy that you pay for. So before you calculate how much it costs to operate a certain device or a certain appliance in your house, the energy has to be calculated. So we have to calculate power times time first to get the energy, and then we multiply that energy by the rate, which is so many cents usually per kilowatt hour, and that equals the cost. And remember that there were a number of formulas that you could use to actually calculate the power. Okay, there's several ways to do that. So let's do some examples of some of that stuff. We'll start again with some multiple choice, and we'll move into some long answer stuff. So a 6 ohm and a 12 ohm resistor are connected in series to this battery. What power is dissipated by the 6 ohm resistor? Well, the first thing we need to know, in order to calculate power, we need to know 2 of V, I, or R. So far, all we know is the R, the 6 ohm resistor. So we need to know either a current or a voltage to go with it. Now, because this is a series circuit, the two voltages, are not going to be the same, but the 2 currents are going to be the same. So the first step here is to calculate the total resistance by saying 6 plus 12, which is 18 ohms. There's the total resistance in our circuit. Now we can calculate the total current. And remember, the total current is also the current in each resistor because it's a series circuit. So V over Vt over RT, V over R. So I've got 36 volt battery, 18 ohms of resistance. That's 2 amps of current, 2.0 to be exact, but I'm not going to worry about sig figs in a multiple choice question. Now I know the current in that 6 ohm resistor. So now I can say power equals I squared times R. Remember, that was one of the formulas we could use. Now we could say that V equals I times R first and find the V, okay, and then say power equals V times I, but I prefer to do it all in one step if I can. So I just say 2 squared times the 6 ohms, and 2 squared is 4. 4 times 6 is 24 watts of power. So the answer is C. The answer is C. Now, the next question says, which one of those is equivalent to 1 watt? Which one of those is the same thing as 1 watt? Well, let's think about the formulas that we use. The main formula for power is V times I. Power equals voltage times current, which is measured in volts times amps. V times A. So that's choice C, isn't it? A watt is the same thing as a volt times an amp. It's also the same thing as an amp squared times an ohm, or a volt squared over an ohm. But none of those choices are there. Okay, volts times ohms. If that said volts squared over ohms, it would have been okay. But that's not what it says, is it? It's just volts over ohms. Okay, so you got to look at them very, very carefully. The volt times amp is the only one that matches. All right, let's try this one. We've got a combination circuit. So it's kind of a combination of what we did in topic 10 and what we're doing now with power. And a lot of times in the circuit analysis question on part 2, they'll also have a part there where you have to calculate the power in a certain resistor. Okay, but in this one it says, what value of R in this circuit, what value of R right there, would cause the parallel combination to dissipate the same power as the 4 ohm resistor? Well, if it's going to have the same power, that means it has to have the same resistance. Okay, same power, same resistance, because remember, it's the same current going all the way around the circuit. So P equals I squared times R. In order to have the same power, I have to have the same resistance, because I already know I have the same current. So, in other words, the parallel resistance has to equal 4.0 ohms. We know that because it has the same power. So what that means is that I can say 1 over 10 plus 1 over R equals 1 over 4. So that means 1 over R is actually equal to 1 over 4 take away 1 over 10, which means that R equals 6.7 ohms. The answer is D. So that's kind of a level 3 question, because it didn't actually ask you to find the power. You had to realize that in order to know the power, we'd have to know current or voltage, and it's the same thing. Okay, it's the same in both, right? Both sections of that circuit, in order to have the same power, would have to have the same resistance. That's it. Let's try the next one. What's the power rating of this kettle if it draws 12.5 amps of current in a 120 volt circuit? Power equals V times I. In this case, the V is 120, the I is 12.5. Multiply the two of those together and you get 1,500 watts. And that, by the way, is a pretty typical power rating for an electric kettle. It's also a pretty typical power rating for a hair dryer, for a toaster. Okay, those types of things are all usually up around 1,200 to 1,500 watts. They all draw a very similar amount of current. All right, next one. A potential difference of 12 volts causes this much charge to pass through a resistor in this amount of time. Now, to get power, remember, I need voltage and current, or voltage and resistance, or current and resistance. I already know voltage, and I got enough information to find current, because current equals Q over T, which is 0.35 over 2.6. That gives me a current of 0.135 amps. Now I can calculate the power because power equals V times I. Right? I know my V is 12. I now know my current is 0.135. Multiply those together, and I get 1.6. So 1.6 watts is the correct answer. Okay, so none of these are terribly difficult. Next one. On the next one, it tells me that I've got a 1.2 times 10 to the 3 watt hairdryer with this resistance, and I'm asked how much current. So I know V, I'm trying to find I. Or sorry, I know R, and I'm trying to find I. So power equals I squared times R. That's the formula I should use. That's the formula I should use. So here's what I do. I know my power is 1.2 times 10 to the 3. I'm going to write that as 1200 because it's easier to write. Equals I squared times 10.0. Divide by 10, both sides. And I'm left with I squared equals 120. So I just take the square root, right? I equals the square root of 120. And the square root of 120 is approximately 11. Okay, it's actually 10.99 something. So 11 amps would be the answer. 11 amps is the answer. Okay, let's try another one. This time we got cost. So we've got a 2.0 kilowatt heater, so it gives us the power. It gives us the time, 10 hours. So now I can say energy equals power times time. So in other words, 2.0 kilowatts multiplied by 10.0 hours, that's going to give me 20 kilowatt hours, which is great because that's the unit I want. I don't have to do any conversions at all. It's already in kilowatts and hours. So kilowatt hours it is. That gives me a cost of 20 kilowatt hours multiplied by 0.11 kilowatts, or sorry, cents per kilowatt hour. And that's in dollars already, you'll notice. So I multiply here, I get 2.2. Now, the kilowatt hours cancel, so I'm left with dollars. So $2.2. So in other words, $2.20. The answer is A. The answer is actually A. Okay, that's the way that one works. That's a cost question. And we're going to do another one of those now in just a little bit on the Part 2 type questions. Okay, so that's it for the multiple choice questions. Okay, and we're going to plug right along here, because it shouldn't take too much longer to finish this off. This guy right here, that's what we call a level 3 question again, because this is a little bit different. It says we've got an electrical appliance running off a 240 volt power supply. So that could be an oven, it could be an electric dryer, it could be a hot water tank, those types of things. And it shows us how much power is used in so many seconds. Well, remember that energy equals power times time, right? Energy equals power times time. Now, because we got a graph, power times time is actually the area under that graph. It's the area under that graph. So that's the way we're going to do it. We're going to say energy is the area. So it's the area, first of all, from 0 to 90. So I'm just going to cut it off right here. That gives me this shape. And then from 90 to 180, it's a different shape. So this is area 1, this is area 2, and they're both rectangles. So all I got to do is go length times width. So I've got 1,000, which is up to here. See, 1,000 times 90. That's the first area. And because that's watts times seconds, that's going to give me energy in joules. Then on the second part, it's only 500 high, but it's from 90 to 180, which is 90 long again. So I got 500 times 180 minus 90. Okay, do that calculation, and there's your answer. We get 1,350 joules, or 13,500 joules, or 1.35 times 10 to the 5. Same thing. Same thing. All right? Actually, no, it's 135,000. There you go. That's better. 135,000. Finally got the right number of zeros. 135,000. That's the same as that number there. Okay, so that's how you do that. You have to find the area. Because the power is not constant, see? Now, you could have done it by saying energy equals power times time for the two different sections. It's the same thing, because power times time is the area. So it's one and the same. Then it went on to say, what would be the resistance of that appliance when its power consumption is 1,000 watts? Okay? Resistance of that appliance. So, we know the power. Let me get rid of that for a second. We know the power. I'm trying to find the resistance, but if you go back, we already know the voltage. We already know the voltage. So I'm going to use the power equation, and I just remembered that this one is already solved here for me, so we may as well look at the solution. So power equals V squared over R. That's the equation that's best to use, because we know the power, we know the voltage, the only thing we don't know is R. So that's the equation we're going to use. We plug in the numbers. 1,000 watts is the power. 240 volts is V. Don't forget to square it because it's V squared over R. Excuse me, when you solve that, the resistance is going to work out to be 58 ohms. Now that was pretty generous on that public exam, that you actually got 2 marks for doing that calculation. If that was a multiple choice, it would only be worth 1 mark. And that would be fairly typical of a multiple choice question. So don't expect anything quite that easy. It's not likely to happen. It does slip by every now and then, but it's rare. All right. This one here is a cost one again. We have a soldering arm with a resistance of 576 ohms connected to a 120 volt circuit. So the first thing we need to do is calculate how much power does that soldering iron use. So we use power equals V squared over R, because we know V, we know R. We calculate that to be 25 watts. That's 25 watts. Now we need to calculate the energy. Now we need to know the energy. But before we do that, because our cost of electricity is given in kilowatt hours, we're going to have to use kilowatts for our power unit and hours for our time unit. So the first thing I do is I transfer my power, or I convert my power into kilowatts. I divide it by 1,000. So 25 becomes 0.025 kilowatts. That's your first step. Now we do the energy. Energy equals power times time. So power was 0.025 kilowatts. Then it says 8 hours a day for 21 days, so that's 8 times 21 hours. Or 21 times 8 hours, however you want to look at it. That gives you a total energy of 4.2 kilowatt hours used by that soldering iron in that 21 days. Now the only thing left to do, now that we know the energy, is to calculate the cost by taking our energy and multiplying it by the rate. Okay? So the cost is going to be 4.2 kilowatt hours multiplied by $0.080 per kilowatt hour, and we get this answer, 0.034. And you can see what this question was worth there too, look. 3 marks in total. One of those marks was for science and communication skills, which, remember, means units and significant digits. Significant digits in this one is 2, and the units are dollars. That's it. Okay, that's it. That's all there is to it. One last question before we end. A kitchen has two 120-watt light bulbs, a 450-watt coffee maker, and a 1280-watt deep fryer operating on the same 120-volt circuit at the same time. That circuit is protected by a 20-amp fuse. What would happen if we turned on a 1200-watt dishwasher in the same circuit? Now, because they're asking you that question, you probably might think that it's going to blow the fuse. So let's see. Let's see what happens. First thing we do is we calculate how much power we have at the beginning. So we add up all the power, 120 plus 120, because there's two 120-watt light bulbs. We got a 450-watt coffee maker and a 1280-watt deep fryer, all operating at the same time. Add all those together, divide it by the voltage, and you can figure out how much current is going through that circuit already. There's already 16.4 amps. The maximum, remember, is 20. We're only allowed to have 20. That's all it can handle. So now we figure out how much more is that dishwasher going to add. Well, when we put the dishwasher in too, that's an extra 1200 watts. That's going to give us 26.4 amps. So you know then that as soon as you turn on that dishwasher, the current is going to exceed the 20 amp fuse. The fuse will blow. At least you hope the fuse will blow, because if it doesn't, you got problems. You're going to have too much current going through the circuit. The wires could overheat. It could cause a fire. But that's what the fuse is there to protect in the first place. Now, by the way, most newer homes, and I'm talking about in the last 20 years or more, now don't use fuses anymore. They use circuit breakers instead, which serves exactly the same purpose. The main difference is a circuit breaker can be reset. You don't have to replace it. That's essentially the difference. Anyway, so in this case, as soon as you turn the dishwasher on, the fuse blows, and then nothing works. Then you have to go replace the fuse, and if you're smart, you'll unplug something. In other words, you won't use the deep fryer and the dishwasher at the same time in that circuit. It'll work fine with only one of those, but as soon as you put the second one in, boom, the fuse blows. All right, so we're going to stop right there. That is power and cost of electricity. And as I said at the beginning of this section, that finishes up electricity. So what we're going to be doing in our next session is we're going to take a look at magnetism and electromagnetism. So good luck with your study. Work hard. Okay, come back here and look at some more of these review topics. I guarantee you it can't hurt. It can only help. Good luck.